Hello and welcome. I am Abdurrahman Al-Qusayr Olo. In this video, I will be presenting my solar energy system design project, which was developed using the PV Sol Premium 2026 software as part of the Renewable Energy System course. The objective of this assignment is to design a complete grid connected photovoltaic system, perform technical simulations, analyze the results, and evaluate the economic visibility of the project. For this project, I select here for this project, I selected a commercial building located in Adana, Turkey, as you see here. As the installation site, Adana is one of the most solar-rich cities in Turkey, which makes it an ideal location for a photovoltaic system. The system is a 3D grid, as you see here, a 3D grid connected BV system with a total installed peak power of 27.3 kilowatt peak, using 60 high efficiency solar panels and one three-phase inverter. All of these details, as you see here, will be covered in the following sections. Okay. Here, I will return to this page later. Right now here, let's start with this project setup. As you can see here on this page, the climate data for the simulation is taken from Adana, Turkey, as you see here, for the period between 2001 and 2020. The data source is Metronorm version 9.0, which is one of the most accurate and widely used global solar irradiance databases. Okay, here the data resolutions used in the simulation is 1 hour, as you see here. Okay. Which ensures high accuracy to irradiance models were applied. The Hoffman model for diffuse radiations on the horizontal plane, and the high and devious model for irradiance on the tidal surface on the panels. Okay, here, moving on the model selection, okay. Moving on the model selection, I selected 60 panels, as you see here, of the model Archlick 144HC 455 watt, manufactured by Archlick, uh, a leading Turkish company in electronics and energy. Each panel has a rated power of 455 watts peak. The panels are installed on the south facing, okay, as you see here. 1 minute, please. The panels are installed on the south facing roof of the building with an inclination angle of 15 degrees and an orientation of south 180 degrees. This orientation maximizes exposure to direct sunlight throughout the year. The total BV generator surface area is 130.4 square meters. Okay, here right now in page number 5. Okay, in page number 5, for the inverter, I selected the here, as you see, inverter number 1. We selected the Connex CL 25,000E version 1. manufactured by Schneider Electric, a globally trusted brand in electrical and energy management system in the world, one of the biggest companies in the world. This is a three-phase inverter with a rated AC power of 25 kilowatts. Okay, 1 minute, please. Yeah. After that, which is here, this is the three-phase inverter with a rated AC power of 25 kilowatts, as we discussed before, and the sizing factor is 111.4 percentage, which is within the optimal recommended range, ensuring the inverter is neither undersized nor oversized for the array. Okay, here in the same page, one of the most critical steps in solar system design is shading analysis. Shading from nearby trees, buildings, or structures can significantly reduce the energy production of a PV system. BV Sol performs this analysis automatically based on the 3D model of the building and its surroundings. Okay. What you are looking at here is the horizon. Okay. The horizon line diagram from the 3D design. This chart shows the sun path across the sky throughout the year. The highest arc represents June, as you see here, when the sun is at its highest point, and the lowest arc represents December here, when the sun is lowest. Okay, here the horizontal axis represents the azimuth angle ranging from north at 0, as you see here, okay, degrees, through east, okay, through east at 90, south at 180, and west at 270 degrees. The vertical axis represents at altitude angle of the sun from 0 to 90 degrees. If there were any shading obstacles, they would appear as a line at the bottom of this chart. As you can see, the horizon line is clean and flat, which indicates there are virtual no significant shading obstacles around the installation site. This confirmed by the simulation result, which show a yield reduction due to a shading of only 0.9. As you see here in this page, 0.9%. An excellent figure for a rooftop installation, as you see here. Okay, now we will return to the same page, number 5 here. Also on this page, you can see the AC mains configuration. The system operates on a three-phase connection with 230 volts between phase here, between phase and neutral, and displacement power factor cosine, PHI of plus or minus 0.98, as you see here. This high power factor means the system operates very efficiently with minimal effective power losses. Okay, now we will go to page number 6. Now let's look at the simulation results. After running the full simulation and PVSol, the software generated a detailed production forecast for the system. I will walk you through the key figures on this page. Okay, here the BV generator, as you see, the BV generator output is 27.3 kilowatt peak. The specific annual yield is 1,532.55 kilowatt hours per kilowatt peak. This means that for every kilowatt of installed capacity, the system produced about 1,532 kilowatt hours of electricity per year, which is a strong result for this location. Okay, here the performance ratio or PR, that means performance ratio, is 82.34%. The performance ratio is one of the most important quality indicators for a solar system. It compares the actual energy output to the theoretical maximum output under idle conditions. A PR of 82% is considered excellent. The industry standard for well-designed system is typically between 75 and 85%. Okay. Here, the total annual, as you see here, the total annual grid export 41,040 kilowatt hours per year in the first year, accounting for initial module degradation. Sorry, the export to the grid is 4,747 kilowatt hours. Inverter standby contribution is only 1 kilowatt hour, as you see here, per year, actually, which is negligible. Okay, one of the most important environmental benefits of this system is that it avoids 15,899 kilograms, as you see here, of CO2 emissions every single year over the 20 years lifespan of the system. That is approximately 317,000 kilograms of CO2 that will not be released into the atmosphere. This is equivalent to planting around 720 trees every year. Okay, here in the next page, in the page number 7, now we move to the financial analysis. This section evaluates the economic visibility of the project over a 20 years, as you see here, a 20 years assessment period. The financial model takes into account the investments, costs, feed, and tariff revenue, module degradation, and inflation in the tariff rate. Okay, here the total investments cost for this system is 40,950. As you see here, 40,950 US dollars. This works out a specific investments cost of $1,500 per kilowatt peak, which is a very competitive price for a high quality system of the size. There are no additional subsides or one-off payments included in this scenario. Okay, the system started operation on May 14. Okay, as you see here, on May 14, 2026, with a remuneration period of 20 years, ending in May 2046. The feed in and export tariff is $0.1633 per kilowatt hour, which is provides steady revenue for the system owner. Throughout this period, the inflation the inflation rate applied to the tariff is 16% per year. Okay. Yeah, here. 16% per year, which significantly increases annual income over time. Looking at the economic performance indicators, the internal rate return or IRR, sorry, is 31.32%. This is an outstanding figure. A project is generally considered a good investment, and the IRR exceeds 8 to 10%. At 31.32%, this project is highly profitable. Uh, the the amortization period, meaning the time to fully recover the initial investments, is only 4 years and 8 months. The electricity production cost is just $0.0542 per kilowatt hour, which is significantly lower than the grid tariff. And the total accrued cash flow after 20 years is 677,000 $125, more than 16 times the original investments. Okay, now in the next page, number 8, here, let me walk you through the complete PV Sol output report. On page 8, you can see the detailed cash flow table for all 20 years, from the first year to 20 years. In year 1, there is a large negative cash flow of minus $33,919 due to the initial investments. From year 2 onwards, the system generates positive annual revenue. By year number 5, the accrued cash balance turns positive at around $4,179, confirming the 4 year, 8 months, as we said before, payback period. By year number 10 here, the accrued balance is already at $94,000, and it grows steadily to $677,000 by year 20, thanks to the compounding effect of the inflation adjusted tariff. Okay, now in the next page here shows the accurate cash flow chart graphically. You can clearly see the dip in year 1, okay, here, followed by a steady climb that accelerates in the later years due to the inflation effect on the feed and tariff. After that, in the page number 10, we will see here, the circuit diagram of the system. The two strings of 2 by 15 panels each connect the MPP inputs of the Schneider inverter, which then connects through the feed and meter to the EC main grid at 230 volts, 3 phases. Okay, now in the next one here, as you see in the page number 11 and in the page number 12. Okay. Show the overview plan and dimensioning plan of the roof layout. You can see how the 60 panels, okay, here are organized into groups across the roof surface with proper spacing to allow for maintenance and air circulation. Okay, and here in the page number 13 shows the string plan, as you see here, the string plan, which illustrates how each individual panel is numbered and connected within each string. This is important for installation and maintenance purposes. Okay, and in the last page here, and finally, page number 14 shows the complete bill of materials, the parts list. This includes 60 PV module, one Schneider inverter, 50 meters of DC strong cable, 4 millimeters squared, copper 30 meters of AC three-phase cable, 6 millimeters squared, a feed emitter, circuit breakers of 50 ampere and 40 ampere, and residual current device rated at 40 ampere with 10 milliampere sensitivity. Okay, now we will return to page number 3. We're here. Uh, to summarize this project, we designed a 27.3 kilowatt peak three-phase grid-connected solar PV system for a commercial building in Adana, Turkey, using PV Sol Premium 2026 software. The system uses 60 Archlick, okay, as you see here in this one. Okay, 60 Archlick 455 watt panels and Schneider Electric 25 kilowatt inverter. The annual energy production is 41,840 kilowatt hours with a performance ratio of 82.34% and a shading loss of only 0.9%. From a financial here in number 7, yeah, for a financial perspective, the project is extremely attractive, an IRR of 31.32%, a payback period of under 5 years, and a total net profit of over 6,707 $677,000 over 20 years from an initial investment of just $40,950. Based on these results, I strongly recommend this type of solar energy system for commercial and industrial buildings in southern Turkey, especially in cities like Adana and Mersin, where solar radiance levels are among the highest in the country. The combination of high solar potential, competitive equipment cost, and a favorable feed and tariff makes this an outstanding investment opportunity. Thank you for watching. This project was completed as part of the Renewable Energy System course using BV Sol Premium 2026 by Valentine Software. And thank you very much again. Thank you.